Dear colleagues and friends, good afternoon, good evening, and good morning. So welcome to the closure session of the fourth Rhineland Microdurability Conference webinar series. There are a few activities in this session. So first, we will have a closure lecture given by Professor Klaas from Breugel, and we will have a best students presentation awards, followed by the announcement of the next Microdurability Conference, and finally is the closure remarks. First is the closure lecture. I would like to invite my colleague, Professor Eric Strong, to introduce the speaker and to moderate the closure lectures. Eric, please.
Thank you, Guang. Well, the closure lecture will be given by Professor Klaas from Breugel, who is an emeritus professor of Delft University of Technology. Well, he's not really emeritus because he's still sitting in his office at the university, as you will see soon. He was leading our construction materials group for many years at the Faculty of Civil Engineering and Geosciences at Delft University. And he was also one of the initiators of this Microdurability conference series. So that's why he is the one that should give the closure lecture for this conference. And the title of his lecture is actually a question. And the question is why cement-based materials could make the difference. And I hope he's also going to give the answer to us because we're also all looking forward to that. So, Klaas, the floor is yours.
Okay, thanks. Okay. I will now go to my presentation with help of some of our students. That is what I need to get it done, to get started. So welcome for this session, and thank you for the introduction, Eric. I will share some of my thoughts with you, and I hope it will be of any meaning sense for you. Indeed, it's a question, why did cement-based materials could make the difference? If I look to the topics of this conference, I've here a list of the different sessions, then there is actually only one that's speaking about cement hydration. And then I see a lot on alkali activated materials and secondary cementitious materials and alternative binders and recycled materials. Well, and then some stuff on degradation and surface life and modeling. So the question is there really some future for cement-based materials, because all the emphasis is on other stuff. But still, I ask the question, where are we going? Where are we going with all our building materials? And I think a realistic speculation about the future should be based on a realistic evaluation of the past. And what did we see when we looked to the past? Well, the structural materials we used in the past were mud and clay, and they were plenty available in big quantities. Then we had wood. And another thing of wood is that it is renewable. And then we have, of course, the natural stone. And just some images of what has been built in mud today, still today, just not only houses, but also whole cities in Afghanistan and also in Yemen and other places there you see many of these mud houses even today, but in the past, of course, even more. Then we have the wood, but that's also been used for centuries. Very old ones, classical ones, but also modern buildings, and even multi-story buildings up to 16, 18 stories are built in wood. So also wood is nice. And then the natural stone with some bridges over 800 years old and even older. So that's what those materials what has been able with these materials. And we can say, if we look back, that there was enough for everybody, enough building materials for everybody and what we wanted to build we could do it. There was enough to meet and realize people's needs and ambitions. But if we look to the future, and even not the far future, but where we are today, then we see an enormous growth of the population. And we have to wonder whether there is still enough building materials for all those people who want to have houses and to travel and so on. It's not only the growth in population, but it also the fact that each individual person needs more. There is an enormous increase in the gross domestic product per capita, as what you see here. And together, these increase in demands for materials and energy and so on of individuals and the population growth ends up in an enormous world gross increase in the world gross domestic product, as you see here. It's enormous. There is not any sign that this will decrease. The need of people, the demand for more materials and more energy is going on. Even certainly when we realize that so many people on this planet are still looking forward to higher prosperity and higher welfare level. Interestingly, this picture shows that cement has played an enormous interesting role in this, an important role. If you look to the red curve, which is here showing the increase in the gross domestic product worldwide, and it's in the time scale from 1950 to 2020, so the last 70 years, then you see that also there is an enormous growth in the amount of cement with this gray curve, and the growth in the consumption of cement is even higher than the growth in the gross domestic product. So we can simply say, and it is fair to say, that cement and concrete has played a big role in the increase in this, well, in our present level of welfare and prosperity. But what that has been able to have those big cities, as you see here, an example, and also big infrastructure works have all benefited and have been were possible because of the use of concrete and of cement. And why was concrete so successful? Well, it was successful because it was cheap. It was made of local materials. It could be executed with local workers. It was environment friendly. Well, there's some doubt about this CO2 stuff, of course, but there's still, it's a nice material. It's not seriously polluting the environment. It's durable, it's robust, and it is, above all, it is smart. And the smartness of the material, I will deal with that more in this lecture. But first, just to show a very nice example of an old structure that is made in concrete, a type of concrete at least, that's the well-known Pantheon, has often been mentioned as one of the big precious design works of the past, structural works of the past. And why was it now so, why did this Pantheon survive? Well, it was because of the appropriate use of the material, cement-based system, kind like that, kind of concrete. It was very nice design, well designed, and it was very well executed. But apart from that, it was also its functionality. Its functionality is also a reason why it is still there, and it's a very beautiful structure. So, because it is functional and it is beautiful, it is also worth to be preserved and to spend money on. So it's not only a materials issue, it is also the architecture of the whole thing that plays a role, and that is considered as an important reason to preserve this beautiful structure. Other structures that are worth to mention in this respect are bridge decks, and it's the result of an interesting study that has been carried out in the United States, showing the performance of bridge decks in different periods in the past century. It is subdivided in 4 periods, and the first period, there you see on the very left that the performance is quite high. And with elapse of time, you see that the performance is actually decreasing, which is a little bit surprising. But let's guess what the reason could be of this decrease of performance. If we look to this old, the first period, there we saw that they used very coarse cement and not much cement per cubic meter. Later on, they used more finer cement, and it turned out to become prone to cracking. And in the last period, there was an increased risk of early age cracking because of high cement use, fine cement, but also of a very low water cement ratio. If we then look back to this first period, there we saw in those old bridge decks that performed so well that they had a very good self-healing capacity. And that's one of the secrets, I think, of cement-based materials. Let's go more in depth to the concrete and what happens when it is loaded. When it is loaded, you see here a piece of concrete loaded, and you see that there are cracks occur. Yes, here you see that the cracks are occurring here. The load is transferred from one to the other side of the sample, and it causes cracks because it's a very heterogeneous material with all kinds of stresses in it, tensile stresses, and concrete will then crack. And the load will be transferred via the aggregates and via the cement paste, and the cracks, but still the cracks are there. How can these cracks occur? Where do they come from? Well, they come from an external load. They come from degradation mechanisms, or they come from an impulse deformation. Let's look to the first one, a piece of concrete under load. If you have this piece of concrete under load, then it is actually a creep test, and we will see what happens. If you load this specimen, then you see an increase of the strain, that is creep, and then at a certain time, it can be that you have, in this last period, an acceleration of microcracking, actually, and the structure fails. So that's due to microcracking under a sustained loading. But we see also something else. Well, here you see the increased microcracking indicated, but we can also look to the strength, not to the specifically, not to the deformation, but to the strength. And then you see that the strength will gradually increase with time due to hydration. But if it hydrates under load, as indicated here on the left cartoon, then you see that in the end, the strength is higher. And that's interesting because in the previous picture, we saw that due to cracking, there was in the end the failure, progressive failure, sudden failure at the end. And on the other hand, you see an increase in strength. And that's very contradictory that a sample that would increase in strength would finally fail. That's a little bit strange, isn't it? So we see that the ongoing microcracking results in increased microcracking, failure under load, or an increase of compressive strength. An increase of the compressive strength beyond a sample, the strength of a sample that was not loaded. So how does concrete manage to perform like this? Well, it is actually self-healing that does that. The self-healing has been studied by one of our PhD students, Guang, and he has been looking in detail to what is happening in a crack, and he modeled the self-healing that could occur in a crack, that was supposed to occur in a crack. And an interesting thing in his research was that around adjacent to a crack, he found that the cement paste was actually densifying due to additional hydration, and degree of hydration that was higher than in the bulk cement paste, a little bit farther away from the crack surface. Suppose now that this is something that happens always, that you have close to a crack some extra hydration, and we looked at a sample where you have multiple cracking, and when a crack occurs, then you see a little bit of extra hydration, and another crack, a little bit of extra hydration, and so on and so on. So then it might become stronger. We know that there is a good relationship between the degree of hydration alpha and the strength. And if there is extra hydration, then you can expect there will be extra strength. If it is not, in the end, the sample will not fail due to, when you have a very high load level, then you may have this progressive collapse as we have seen in the previous one. But at a moderate load level, this might then happen, that you have an increase in strength. When we look to a strain test, then the following could be the result of self-healing of a microcrack. Suppose you have here in the yellow curve the real creep indicated with this or calculated with this formula, a well-known formula where we can calculate the creep in a not cracked sample. Suppose that you have during the test some hydration, then the creep will decrease because the stress-strength ratio is decreasing. Suppose that you have microcracking. Microcracking will cause an extra deformation. But if the cracks are healed and the material becomes stronger, then the effect of self-healing would be that you have a decrease of the creep strain compared to the creep calculated with the yellow curve. So it would be interesting to see whether it works like that and if we can model that. Well, that has been the work of Wenjuan Yu. She did a study a few years ago. She said, okay, I've here the concrete, on the mesostructure of the concrete. I simulate the performance with a lattice model, and I assign to the cement paste the possibility to crack, but also the possibility to self-heal. You see a close-up of what happened around the crack. Here you have the crack. You have here around the crack some strengthening due to additional hydration. So suppose that you have a crack on the left picture, the right cartoon. The crack is indicated with the red lattice beam. Suppose that you are cracked, then the beams around will strengthen due to additional hydration. That's the idea. Well, this has been put in a model, in the lattice model, and she did the calculations on the creep strain of tests over a period of 30 years, simulating tests of Brooks, who did the tests in 1975 already. And what she found is that if you look to these strain curves, that there is one curve with no microcracking. That was this curve. Then there is a curve with the microcracking. Then you have extra creep. And if you then take self-healing of the cracks into account, then you see a reduction of the creep compared to the creep calculation where you have no microcracking. So you see that there is a trend simulated that is also expected from the conceptual performance of a cracked material, that cracks would, the material, the cement paste around the crack would experience some additional hydration, giving an overall increase of the strength of the material. What you also found that this increase in the strength, this additional extra increase in strength beyond the strength that you would expect from the normal hydration, that the increase of strength was calculated with the blue line as a trend line, and what Brooks found was actually the green line. Well, there's a big scatter in the test of Brooks. You can forgive it because the tests were actually not performed with the purpose we were using them for. So, but I think the trend is certainly the same. So that was nice. What do we learn from this? Well, we learned from this that concrete, looking to the total to all what has been said so far, concrete has played a crucial role in the economic growth. We further have seen that concrete during its lifetime is a system in evolution. It is hydrating, it is cracking, the cracks can heal, or if they cannot heal, there is not enough power to heal them, then you have progressive collapse. But during its lifetime is a system in evolution. And the remaining unhydrated cement gives concrete its robustness and its self-healing capacity. But that's so far it's nice, but still the image of concrete is not that positive because the CO2 issues, I cannot deal with that today, but we all know that. We have also seen that there is enormous growth expected, and that means also an enormous growth in demand for materials. And therefore we foresee shortage in cement and also in sand and aggregate. That's not so often mentioned, but there are many places where there is really a shortage of good sand and good aggregate. And for that reason, it might, and that's a trend today, that we try to use not that much cement anymore in our concrete because it is, first of all, because of the CO2 issue, and secondly, because it is expensive, and then thirdly, there is maybe not enough. So we reduce the amount of cement in our concretes, but that means that we also take away some of the robustness of the concrete. If we do that, then we might be smart to introduce artificial healing components, healing potential into the concrete, for example, by using bio-based self-healing concrete, putting bacteria in the concrete that are able to heal the cracks once a crack occurs and water is available for them to become active. You see here an example of our colleague Henk Jonkers, where you see here on the top, the two top pictures, a control concrete that is cracked, and after a test where water is running through the crack, you see that there is still a crack, there's no healing. But if you have some bacteria in the concrete, then before the water penetration test, there is this crack in the concrete, and after a while, in only a few days, the crack is completely healed because of this capacity of the bacteria to fill up the cracks with reaction products. Another solution for dealing with our shortage of cement and other components of the concrete is recycling. Well, that's a big thing today. Of course, we see here how it works. Well, it's actually not difficult to understand. We have here the raw materials and we have energy. These are actually the two input parameters and input quantities for making materials, for making structures. And then once structures are there, we have the maintenance period, renovation, demolition, separation, and then back in the circle again. Well, when we, in a society where we have something to recycle, that is in, let me say, a mature Western society, their buildings can be used to, as an input, existing buildings and old existing buildings who has to be demolished can be used for as another source of raw materials that can be, or material that can be used in the materials and building cycle. Well, this has now been one of the trends and that work and can solve part of the problem of scarcity of building materials. When we now look to the future, then we see, and it's good to realize that and we look to the money that will be spent in the building sector in the coming decades, then we have to realize that 50% will be spent on, let me say, preservation or consolidation of our existing building stock. And 50% is needed for growth, particularly growth in developing countries. And if we realize that, those two 50% for consolidation and for growth, and we concentrate on the growth aspect, the growth part, and we are going for sustainable growth, then we should realize that recycling is there not an option. When you need growth, then there's nothing to recycle yet. Because you have to build new. You have to use new building materials, new, more and alternative building materials, maybe. To use not too much of these new materials and to reduce the demand for these materials, we should go for smart design, use less materials, and maybe printing, 3D printing is one of the options, is certainly one of the options to use less material. And go for a long surface life. And that means if you go for a long surface life, you will reduce the replacement costs. And you can realize this long surface life by some built-in self-healing capacity, which make the structures more robust and reduce also the maintenance cost. But even more than that is, I think, that we have to reconsider our needs and ambitions. Because if our ambitions are growing sky high, as we have seen in one of the first pictures, then it will be impossible for any material to meet that high demand. In conclusion, concrete can make a difference because it has proven to be able to make a difference in the past. It is highly recyclable, and thus it can reduce the need for new materials. And concrete can be designed as a smart and Smith system, robust, and with which structures can be built with a very long surface life. But more importantly, in view of the sustainability development, sustainability is more than just using smart materials. Think about the Pantheon, where also functionality, architecture plays a role. That also determines whether something is worth to spend money on and to preserve it. The purpose of growth is not growth, but should be maturity. That's what we learn from nature. Nature teaches us that growth beyond maturity is rather a disease than progress. And that means, that brings us to the final thing, that defining the mature society is one of the biggest challenges, I think, that is ahead. If a maturity is only going for growth, and with no notion of what maturity should be, then there is no end in this vertical curve that is going to nowhere. Vertical curve representing increasing growth, but also increasing consumption, and that is not sustainable in the end. Well, those are my thoughts that I wanted to share with you. I see that I'm a little bit over time, so it's time for me to stop here. Thanks for your attention.
Okay, thank you very much, Klaas. I don't see yet questions in the Q&A screen, but you can still put them there. So I will start with one question myself. So you said that circular economy is becoming very important, that we are going to, we want to reuse elements, and also we have to recycle materials because our structures are aging and probably they are, there's degradation of the structures, and then we want to recycle them. But probably if we have degradation, they're also contaminated, the materials. So if we crush them and make new concrete, probably the quality will be less because the materials are contaminated. is there then even more need to design for self-healing, that we can indeed make them better for their next life? Is that something that will be more needed?
Yeah, I think that's true. Well, I went very quickly through that slide showing this recycling. And I didn't mention, I tried to find my presentation back. How do I do that? Yeah, here. If you look to this presentation there, you see, I did not mention that, but that we have here also a materials passport and an element passport. The material passport is actually indicating, let me say, it focuses on a procedure and a procedure that is absolutely needed for taking up new materials, other materials in the building cycle. Because if they do not meet certain criteria, then they might pollute the material cycle. So that's one thing. We have to be very careful by accommodating and mixing material streams, because they can result in a cocktail of materials which are not compatible and can do worse than instead of solving a problem. So that's one thing. And the other thing that you focused on and asked, well, shouldn't we therefore concentrate more on the self-healing potential so that we can keep our infrastructure in good shape for a longer time? I think that's, in my view, a very important strategy for the future. But it should go hand in hand with a good architecture and good planning and a good functionality of the structures. So it means that we have to think twice before we start building things and try to make it flexible and demountable so that it can, when the boundary conditions change or the demands change, that you can adapt to new questions or new boundary conditions set by the society.
Yeah.
Then, is that the sort of an answer?
Well, that I accept that as an answer. Thank you.
Okay, that's fine.
There are some questions in the Q&A screen. So one is from Wadong, and he asked if he would use finer cement particles or reduce cement content. That's what we use now, and it appears that we got more early age cracking. Would it be a solution to go back to coarser cement to solve that issue? Yeah, maybe we also get more self-healing then.
Yeah. Well, that's always a trade-off. Yes, a trade-off economically, but also a trade-off from the perspective of durability and redundancy. If you have more coarse cement, then you have actually more self-healing capacity in your concrete. It has another advantage that you have generally a slower hydration, which is also in the beginning, the early age stage, beneficial because your hydration, your temperature during hydration will be lower, so you have lower stresses and less microcracking. So that's also positive. On the other hand, and that's the thing that is often mentioned, if you have coarse cement, then you have so much not used cement in your concrete. And today some people say, I would say, that when you make concrete with a lot of unhydrated cement in the concrete, then it is a waste of material, because you should use all your material to its full extent. Well, on the short term, that might be then a solution and the reason to go for finer cement. But on the long term, when you have a structure that has less self-healing capacity, it cannot be on the long term be not a less durable solution. And you have to pay the bill later on. Another thing is the use of fine cement and a faster cement is very much dictated by the demand from the industry or from owners or from whoever that want to build as fast as possible. That's something we dictate ourselves, because nature does not ask that from us to be so fast. But that's that's the society we live in.
Yeah. And then there's one final question by Changwen Zhao. He asked, do you think approaching maturity is more a societal problem or a technical problem?
Approaching maturity is more a societal problem. It's not a technological problem. I emphasized that in my last comment. I said, well, defining what a mature society. It's actually a question: what is enough? Yes. What do we need? What are really our needs? In the Brundtland document about sustainability, it says that the well-known phrase that we should not use this planet in such a way that there is nothing left for next generation, but also the next generation should be able to meet their needs. But it's for our generation and for next generation. The question is, what are our needs? What are really our needs for in a way that we can say this is sustainable? And today, looking to this growth curve from the beginning of my lecture, I cannot defend that what we are doing today in the last decades, that is sustainable.
Mm-hmm.
Okay. So this would be my answer on this question.
Okay, maybe one small one, because I like that. What do you see as trends on the nanoscale? What can nano bring us in the future? Maybe that's the last one to end.
Yeah.
And then I give back to Guang.
I think nano can bring us, certainly, it helps us to understand and to design our materials in a better way. I think that there is a big future for that research and for a better understanding of how and why our building materials perform as they do. A big challenge will be how to implement that and to upscale those new insights in the practice. Certainly for bulk materials. On the other hand, for bulk materials, very small steps can already have a big impact, because if you have bulk material with a small improvement, you can, because of this big amount of material that you use for bulk materials, you can in absolute sense save a lot, yes, or reach a lot.
Mm-hmm.
So my answer.
Yeah. Okay. So, Klaas, thank you very much for this very interesting lecture. And I think you have to stay online for a little while. You have some more tasks to do. But
Yeah, I saw.
Back to Guang now.
Okay.
Okay. Thank you very much, Eric. Thank you very much, Klaas, for your inspiring lecture and the discussions. And now we come to our next program. So next session must be very exciting, because in this session, we are going to announce the best students presentation awards. You may ask, why do we set up this Best Students Presentation Awards? Now, this was because we found more than 75 presentations in the conference were given by young researchers. So in order to encourage our young researchers and to recognize their contribution in the research field of cementitious materials, the conference organization has decided to set up the Best Student Presentation Awards. You know, we didn't make an announcement for this competition when the conference started in the very beginning, because we want to give a surprise to the attendees in the closing sessions. So that's why. You may also ask, what is the selection procedure? So in order to guarantee a fair selection, we'll first ask our session chair to nominate the best student's presentation from each session. It was so hard for the session chair to pick up one best because of all presentations was very good. So finally, they provide their nomination. So you can see this is the nomination from each session. So we have in total 18 nominations. Now, another challenge is how we are going to select 5 best student presentation from these 18 nominations. In order to do so, a jury was appointed by the organizer. So there are Professor Karma Andretta and from Polytechnic University of Catalonia, Spain, and Professor Laura Pietro from Empire, Switzerland, and Professor Yamei Zhang from Southeastern University. They are all the members of the scientific committee of the conference. Now, I would like to invite Professor Karma Andretta to tell us how they made the selection and what criteria they followed. Karma, please.
Thank you, Professor Wang Ye. Well, first, it has been a pleasure, an honor to be member of the jury. It has been very interesting, a possibility to analyze more in detail the presentations. I would summarize saying that first we were thinking in the presentation itself, and we found that all were really very well done. I mean, all the students presenting, they have been very ordered, just presenting the objectives of the work, the methodology, the conclusions. In that case, the quality really in this Congress has been very high in all the cases. After we were thinking about the difficulty of the subject, there are subjects that are more difficult for a student to deal with. And there we try to select some of the candidates. And the other criteria has been the innovation, how much the work is contributing for new perspective, new ideas. And finally, how the conclusions have been drawn up. And both innovation and conclusions together with the difficulty has been the basis for the selection. I think that this is the summary, Professor Wang Ye, of the criteria on behalf of the jury.
Thank you very much, Karma, for telling us this procedure. I know it was very hard for jury to make this selection. So now it's a time to disclose this secret. Before to do that, I would like to invite Professor Klaas van Breugel, together with Professor Jiaping Liu from Southeastern University. He also is the Vice President of the Schubert Construction Materials Company, to announce the Best Students Presentation Awards. So, Klaas, please.
Yeah, thank you, Guang, for this, for inviting me to disclose these secrets. Actually, as we have heard, that the real work has been done by Professor Andrade and her colleagues, and I have the honor just to say what the outcome of it is. And well, the first awarded person is André Silva from the University of Lisbon in Portugal. And the title of the presentation is Influence of Carbon Dioxide as a Mixture Component on the Cement Hydration. So, congratulations.
Okay, thank you, Klaas. Next, I would like to invite Jiaping Liu.
Okay. The next winner of the Best Student Presentation Award is presentation to Kai Yang from Ghent University, Belgium. The title of the presentation is Where also enriched water increase the durability of concrete. Congratulations.
Okay, next, Klaas.
Okay, then the third one. That's again from the TU Delft, I see. It's not my, I've not been involved in the jury, so I'm just doing my task. It's Claudia Romero Rodriguez. And the title of the presentation is Accelerated Carbonation of Ordinary Portland Cement Paste on the Microstructure and Transport Properties.
Thank you, Klaas. Jiaping, please.
Yeah, okay. The first winner of the Best Student Presentation Award is Xiaoxiong Ye from South University, China. The title of his presentation is Site Observation of Tricalcium aluminum dissolution in water. Congratulations.
The last one, Klaas.
Yeah, then I have the last one, and that's an award for Mr. Zite Zhang, China, but from Delft University of Technology. And the title of his presentation is Development of the Strain Hardening Geopolymer Composite through Micromechanics Modeling. So, congratulations.
Thank you very much, Klaas and Jiaping, for announcing the winner of the Best Students Presentation Awards. Thank you very much and congratulations to all the winners. So we have prepared some prize for the winner. So the winner will receive, of course, certificates. Besides, they will also receive a JBL wireless earphone and one free registration for the 5th Microdurability Conference. So you may ask, when is the 5th Microdurability Conference? So we're going to announce very soon. So the prize was sponsored by Schupperter Construction Materials Company. Thank you very much, Professor Liu, for your sponsors. Thank you. And I would like to congratulations again to all winners. So before close this part, I would like to ask the winner to send me your home address so that we can post the prize to your home. Thank you. And we are going to communicate with you. Thank you very much. So now we'll go to the next session of this conference is about the announcement for the next Microdurability Conference. Since the Microdurability Conference has received increasing attention in the past decades, and the topics of the conference were relevant to the current social demand, so we have enough reason to continue the success of the Microdurability Conference. Now, I would like to invite Professor Miao to announce the 5th Microdurability Conference. It is very pity Professor Miao today, he cannot join the meeting online. We will play his pre-recorded video.
Ladies and gentlemen, the 4th Random International Conference on Microstructure Related Durability of Cementitious Composites Microdurability webinar is going to close successfully. And at this moment, we miss our beloved Professor Changwen very much. Professor Changwen, Professor Klaas, Breugel, and myself initiated and organized the first Microdurability Conference in 2008. The Microdurability Conference provides a good communication platform for the discussion on concrete microstructure theory and durability improvement technology. I would also like to thank Professor Guang for organizing this unique and fruitful online international conference on the subject serious situation of the COVID-19 epidemic. I believe that our participants will enjoy the Microdurability webinar. Thank you, all participants, for your wonderful report and enthusiastic participation. In 2024, we will organize the 5th Microdurability International Conference. I propose that Professor Liu Jiabing and Professor Guang co-chair the organizing committee of the 5th Microdurability International Conference. The specific work will be carried out by Professor Liu Jiabing. We will learn from Professor Guang's successful conference experience and organize the next conference well. It is anticipated that by that time, the COVID-19 epidemic should be well controlled, and we look forward to the world in return to normal, and we look forward to meeting you in Nanjing in 2024. At last, I wish our participants happiness. Thank you very much.
Thank you, Professor Miao. According to Professor Miao, the next Microdurability Conference will take place in 2024 in Nanjing, China. We're really looking forward to that. Now we come to the next part of the last part of the conference. So we're going to make a brief review on the Microdurability webinar conference. As you see, the Microdurability Conference will have in total 18 sessions, spread into 9 days within 1 month. We have 125 papers has been presented and discussed in the conference. The topic covered hydration, microstructure, transport, degradation, recycled materials, alternative binder, and new technology. We organized 3 special sessions, so alkaline activated materials, alkaline silica reaction, and carbonation. From the presentation and the discussion, we realized that the worldwide mission on lowering the global CO2 emission has pushed us to looking for new or alternative binder to partially or fully replace Portland cement in construction. when we introduce new binder in concrete, they will have a different hydration mechanism and microstructure development. This may cause the new durability problem. So the safe life of concrete structures made of new binder has to be investigated. In this conference, we also present a lot of new information about new technology, like 3D printing, smart materials, machine learning in numerical simulation are used more and more in construction materials. All these aspects open a new possibilities to researchers. International collaboration, exchange research experience are very important for us to build up a better society. The Microdurability Conference, all presentation videos were uploaded to the Microdurability webinar channel in YouTube and Bilibili. You can easily find by searching Microdurability webinar. I think this is very helpful for the attendees who have missed a session. It is easy to catch up the details by watching this video. You're also very curious and want to watch the video from the Best Students Presentation Awards, where we are marked on the title of this presentation on the website. You can look at it. A lot of others asking about the conference proceedings. So actually, the conference proceedings is ready for publication. It was very pity that this time the proceeding cannot be published by Ryland because of we didn't ask the copyright from others. Instead, the proceeding will be published as like open access by the Library of Geodeft. We will release the proceeding very soon in the beginning of June. It is fair to say the microdurability was a big success. So in this special COVID-19 pandemic period, so many people have contributed to in so many ways to turn these events into a smoothly running webinar series. First of all, I would like to thank to our scientific committee for reviewing the papers, chairing sessions, and leading active discussion and selecting the best students' presentations. The valuable efforts ensure high quality presentation and high scientific quality of this conference. My great appreciation goes to the keynote speaker for taking the time out of the busy schedule to deliver excellent keynote lectures with a great scientific value on the pre-conference webinar last October. And thanks for joining the panel discussion to sharing the view on the microstructure durability and further research in construction materials. I also would like to thank to the special session organizer, Stan, Zhonghua, Maria, and Zhongguo. Your excellent work brought new atmosphere to the Microdurability Conference. We were very glad to have an alkaline activated materials special session jointly organized with a dual middle term workshop. It was a successful experience for both of us. I'm very grateful to the microdurability team, the PhD students, and the postdoc researchers from my research group for the enormous and high quality support. Dr. Donghua, he started working on the microdurability conference 3 years ago. He communicated with the authors and to track all the papers, edit the conference proceeding, together with Breugel and Liu Chen. Abina, her active communication with the presenter guarantee that all videos were received on time. Our Zoom host team, leading by Shijie and Jiayi, including Louis, Changwen, Liu Chen, Hama, Changwen, and Yu Zhen. Behind the screen, they work very professionally to keep the webinar go very smoothly. It is unbelievable that our Zoom host team made almost zero mistake throughout the whole webinar period. Iris, our conference manager, she has worked very professionally in registering all participants, interacting with them on many details. I also would like to thank my colleague Breugel for his contribution to leading the panel discussion together with Eric. It was a very interesting discussion. My special thanks go to Professor Miao, Professor Liu, and Professor Zhang from Southeastern University, and Eric Klaas from TU Delft for the great support throughout the conference. They are the solid backing of the conference organization. Ryland, FIB, ACI are thanked for sponsorship, especially thanked to Ryland for many years' support on microdurability conferences, and the Schubert Company for sponsoring the prize. Last but not least, I would like to thank to all attendees. You have spent your valuable time and efforts to prepare high-quality presentation videos and submit it on time. We would like to thank you all for your great scientific input and for many fruitful discussion and scientific interactions. Without your attendance, the microdurability conference is not possible. Excuse me, I cannot list all presentations here. In the end, hopefully we can meet each other in person very soon, and I wish you good health and stay safe. In the end, I would like to close my remarks and officially announce the end of the Microdurability Conference webinar. Thank you very much.